Thank you, Chairman. Thank you for the introduction. I think I can manage it for this, so we'll do a little bit there. Thank you for staying with us at this last presentation. It's certainly a relief for someone sitting that long. So first of all, we're trying to put you in a perspective what we are doing here and where we are with our research. So we are here in a low resource devices, or these embedded devices, where we want to apply techniques of implementation of microphone grids, microphone arrays, apply in the modern consumer electronics environment. So we are thinking that this microphone grid can benefit a lot with the intelligence of this modern consumer environment, so that we can actually monitor a lot of stuff and do some intelligent decision only based on recorded sound. There are many problems with that, of course, but the key advantage of acoustic sensing in this way is that you don't have to be in a line of sight with the event that you're trying to detect. So it actually works for unconventionally shaped rooms or dealing with some obstacles and all that, because sound is propagating really well with the closed environment. And some of the benefits that we are trying to do and bring to our advantage here is cloud computing and advancement in this area, and a lot of this embedded and small devices, small scale devices that are coming from recent development from IoT. This is going to be a short and simple presentation of some of the engineering work that was needed for our complete research. But so far we've done some voice communication and voice analysis and voice command systems, and we also did modeling of acoustic environment in this reverberation environment. And also we presented work that is actually fully cloud-based voice interface for Internet of Things, with a example of a tiny device that actually speaks to Google speech-to-text service. So what's the main idea behind this work is to actually develop a server application and to explore how architecture in the server application can benefit from all these applications we mentioned before. And we want to make it simple so that we can do a heavily extension of it in future, and we want to base it on well-known techniques and well-known software solution, like web-based interfacing or these well-known communication protocols like RTSP and RTP. For those that don't know what those are, RTSP is a protocol for controlling all the multimedia devices, so you can connect your device and do a playback or stop the device to RTSP protocol. And RTP protocol is simple read-time protocol, which is sending the packets of data with a time step information and a little bit of sequencing and providing your basic needs of serialization data is sending to some carrier. So we will speak about the server and the system architecture that we have in mind. We will discuss a little bit about the wireless microphone nodes that we use and give you an overview of the user interface that is designed. And we are looking at this system, the proposed system, trying to do a performance analysis and how good is this working in the real environment when we're trying to communicate over the internet, or when we are trying to apply this in a house where we have a simple Wi-Fi router and a couple of these microphone nodes. and we'll glance over what other people do, and finally close with the remarks. This is the server that we have in mind here, and it's basically a centralized server that all the microphone nodes are communicating with. So this is a sort of a star topology in the system. And we base this server on Apache web server and use a Live 555 streaming library to actually communicate and stream all these different audio streams that we're coming to the server. Then we structured our server to accommodate variability of audio processing, and we implemented just these two. But we currently have more of these processing algorithms and trying to combine the data of various microphones. So this is the general system architecture where we have nodes on the one end which are constantly recording sound, and inside of each of this node is a little bit of a noise gating, which is implemented in the modeling of the related work that I showed before. And then all those nodes are communicating through this RTP and RTSP protocols to server, which is offering an RTSP server, and this DSP module is actually DSP modules, which are streaming in a filter fashion, like cascaded filters of our processing streams, and we're able to combine them to make some sort of intelligence on top of that. Then we extract this information and exchange it with this data exchange model through JSON packets, communicate with any web browser, and show data that is calculated on the server. This is how we started in some of the earliest work. We started with an XMOS device, pretty powerful one, with a multi-core device and an 8-core with really hardware threads. We connected that to an encoder board, which has a microphone connected to it, and communicate to this now old Wi-Fi module, which is actually based on the TI solution that we are currently using. Now we skip the XMOS part and have a more advanced microphone node based on this CC 3200. Previous version was on the 3100 device, which is now programmable, so we can actually program our RTSP and RTP protocols inside of such a device. So we have Wi-Fi communication and a little bit of formatting and forming an audio stream inside of such a device. On the bottom, you have a smaller form factor of such a board, so it can be even smaller than what we use here. This is in a launchpad, which is extendable and sort of a generic for any IoT application. And these microphone nodes that are enabled over IP are going to be much smaller than this. So this is a simple user interface where we are trying to compensate imperfection in the microphone, because we have a DC signal, for instance, because of the really cheap electronics and really cheap microphone used in this platform, so we need to remove the DC component. And then we are just calculating the loudness so that we can plot it here as an example of the system. And this is a system monitoring 4 different rooms, and we can see a level of noise or level of activity in each room just by logging into a web server by any web browser, either from mobile phone or from desktop. For presenting all this, we use this multi-chart library, which is really doing well. With it is a JavaScript library for this for the presentation temporal data which we have in this graph. So this is a performance evaluation in a closed environment. This is the one flat where we have positioned a server which is connected to the Wi-Fi access point, and we have 3 microphone nodes connected to a server through this AP. And depending on the obstacles and depending on interference and actual noise on the Wi-Fi spectrum, we get a different results from each of the nodes. We are monitoring here the percentage of data loss. And for 16 minutes, you can see that we lost in total 14 seconds, for instance, which is 1.45% of our complete audio. This is where we don't apply noise gating. This is when we continuously stream for 16 minutes and just measure whether we are able to receive all the packets through the system. Then we wanted to see how this is behaving over the internet. We choose some random path and by choosing 2 different internet service providers. So you can see the routing of the packets in the picture above. And there we also achieved a pretty decent results. This particular line was stable enough for performing even better. So probably in this setup and in this environment, we had a problem or some serious interference with sensor number 3. And it also can be that our embedded platform is misbehaving, and that particular one is just doing something weird in the radio. So that's what we get experimentally. Of course, all this related work will eventually lead up to solutions like Google Now or Hello Google, famous application, where you want to speak your command or your query inside the room, and you get whether is it outside or some kind of forecast or some other information. There is also a counterpart in Siri coming from Apple, and all these also echo device from Amazon and this voice pad for communication and integration with the smart houses and all that is used by a lot of different vendors, but all these systems are closed and you cannot really have the documentation or do something fun with it other than what company meant is a primary application. So we're still looking for a good solution. This is now in the right bottom corner. This is a new Xbox platform with a microphone grids that is connected to the internet. So we are looking for a better platform where we can do much better sound acquisition, and also we are challenging some of our systems to make advances in our future work. So we can conclude that this system works and has a good foundation and good potential for some future application. It sits alongside with all the research that I showed up front with this voice communication, this modeling of such a traffic. But what we have in mind for the future work for sure is to experiment with the compressed audio formats, because here we only use uncompressed PCM, 16 bits and 60 kilohertz. We want to explore a bit more, and there are a bunch of related work using much more aggressive coders to actually do the transfer. And this is really essential if we want to apply these techniques to different network topologies, when these nodes have to relay to this data, so that we then speak about many different communication problems. So this is all going to be a focus on further analysis. And that's about it.
Questions?
What's the main component of delay in the system? Was it the audio processing? The overall system, if you even consider the web server?
Yeah. So delay currently comes from buffering and processing this. So basically, if we want to apply different complexity of algorithm here, we have to collect data upfront to actually feed the algorithm. This is really simple one, and the latency of this is in milliseconds. Of course, if we are talking about application of communicating through internet, then the round trip time is again a factor, but we have not done that kind of analysis because it depends on an application. We just looked at the two experiments and got the results, and we are really interested in the quality of audio and what we can actually expect from the system like this. So cheap embedded device connected to well-known server components and architectures, and what kind of environment we are getting out of all these components.
Can I ask another question?
Sure.
This topic, the data exchange. You said you use the JSON format. Is it optimal, or is it because the Apache
So
could that also affect
no.
in any way the processing this data format?
No. So this JSON format is just for us to decoupling web server and our mini communication server.
Comes after the processing.
Yeah. So this is really small, and it should be really simple. Depending on what we want to visualize, it can be much bigger, but then intelligence here can be much more complex. So again, I think this is not a very good. So this is just when data is processed to get the RMS value of all these IP of the microphone or packet loss and all that. So this is just for exchanging the web server side.
Any other questions? So let's thank Davor.